Okay, this is the second video on the rotational kinematics. And what we want to do is very similar to what we did back in the linear kinematics unit, and that is we want to list out all the variables that we know as we read so that we can use those variables and then figure out which equation to use. So if you take a minute to read through this problem. A bicycle wheel begins at rest and experiences an angular acceleration of 0.6 radians per second squared. Now, something that they mentioned briefly, but it was hard to catch if you might not have caught it, and that is what its initial velocity is. It starts at rest, so its initial velocity is 0 radians per second. And it says it's going for 8 seconds, so our time is 8 seconds. What is the final angular velocity? That's what we're looking for. And what is a linear displacement? So let's talk about part A first. And so we're going to go up here and we're going to look at our equations and we're going to look at which equation should we use. We have an alpha, we have the initial velocity, we have time, we are trying to find the final velocity, and so we're going to choose whichever equation is going to work. And I think this top equation is going to be the best one. So our final velocity is going to equal the initial velocity plus the acceleration times time. And of course, our initial velocity in this case is 0, so we don't even need that. So we have our final velocity is the acceleration, which is 0.6 radians per second squared, times the time, which is 8 seconds. And so we just need to multiply that out. And if you don't have a calculator yet, make sure you get a calculator so you can do these calculations as we go. And when we do this, this is one we can probably do in our head, we get 4.8 radians per second. I'm sorry. I was pausing because I was looking at my units. And with my units, I have radians per second squared times seconds. So that second cancels out one of those seconds, and we get radians per second. So the answer to part A is just 4.8 radians per second. Part B says, what is the linear displacement if the wheel has a diameter of 68 centimeters? Well, if the diameter is 68 centimeters, then the radius is 0.34 meters. And so we need to figure out what we should do with that and how we need to find the linear displacement. Well, I'm going to say that before we get to linear displacement, why don't we find angular displacement first? And so let's find that angular displacement by using the second equation. And so to find angular displacement, we know that our initial velocity was 0, so we don't need that. But this is going to give us our angular displacement pretty easily. We're just going to take 1/2 times the acceleration, which is 0.6 radians per second squared, and multiply that times our time squared. So go ahead and take out your calculator and multiply all that together. And we should get 19.2 radians. Now, that is the angular displacement. It rotated through 19.2 radians. And the question is, okay, well, if we know what the radius is, how can we change that into linear, into meters? I'm running out of space, so I'm going to come over here to the margin to do that section of it. Let me walk you through a little bit, and then we'll be able to come up with a kind of a generalized formula that we can use. And I don't think this formula is on the formula sheet, but it might be again. But let's just kind of go through how we derive it so that we can use it. If we think about a circle, and a circle's circumference is 2 pi r. And so the circumference of this wheel is 2 pi r, or in other words, we could also call that pi times d. That is a radius, a circumference, but as it goes, it's going to lay out a straight line. And so that's what we're talking about here is, okay, if it rolls, what is the straight line that it's going to roll out and show us? Well, we also know that a circle, as far as radians go, a circle is 2 pi radians. So let's rewrite this that 2 pi radians is equal to For our circle that we have, it has a diameter of 0.68, so we can say 0.68 pi. Now I'm looking at this equation and I can cancel my pi on both sides. I can divide by 2 and I get that a radian is equal to 0.34 meters. And so if this travels 19.2 radians, I can take that and I can multiply it by 0.34 meters because there's 0.34 meters in 1 radian. That's what I have over here. Look, I have 1 radian is equal to 0.34 meters. And so now my radians cancel. And so my linear distance is just 19.2 times 0.34. And that answer comes out to be 6.5 meters. And so the generalized formula that I was talking about is going to be that if we take our theta, the displacement in the angular displacement, and we multiply that times the radius, it will give us the linear distance. And I think in our book they use a S for that, but that's not something that we use with AP is the S, and so I'm reluctant to use that. I'm just going to write it out like this, that if we take the theta times the radius, that will give us the linear distance. And like I said, I don't think that's on your AP sheet, but it's pretty easily derived, and you can easily do it on whatever problem you're working on, but we can kind of generalize it. If you want a formula for it, this is going to be a formula that you can use that for. Okay, let's look at question number 2. The thing about question number 2 is that we are measuring in revolutions per minute, and we really want to do radians per second. So I'm going to take a little bit of time to come over here in the margin and take 850 revolutions per minute, and I'm going to change that to radians per second. And so I have to think about my unit conversions and what that's going to be. Well, I want it to be in radians per second. So I want my seconds in the denominator, and there are 60 seconds in 1 minute. And I want my radians to be in the numerator, and there are 2 pi radians in 1 revolution. So that's how I'm going to set up my conversion. And so now I just have to take 850 times 1 times 2 pi and divide that by 60. So once again, get out your calculator and calculate that, see what you come up with. Okay, so when you do this calculation, you should get 89 radians per second. And so that is our initial velocity. Then we also have that it turns 1,500 revolutions before coming to a stop. To change that to radians, we need to multiply that times 2 pi. So take a second to do that. And that's our distance. That's our theta. That is the displacement that it has gone. And so when we multiply that out, we get 9,424.8. And that is in radians because we converted it from revolutions over to radians. So we have our theta, we have our initial velocity. We know our final velocity. It's coming to a stop, so that's 0 radians per second. And so now we need to look up above and decide which equation that we're going to choose to find our acceleration, because the question is asking about acceleration. So as we look up there, we need to use this third one to determine our acceleration. So I'm going to use that equation. Our final velocity we decided was 0, so that's just going to be 0. Our initial velocity was 89 radians per second. We need to square that. And so we take that plus 2 times alpha, that's what we're looking for, 9424.8 radians. So let's go ahead and square that 89 to the second and bring it over to the other side. And so we have a negative 7921. And on the right-hand side, we need to take 2 times that 9424, which gives us 18,848. And so when we divide that, we get an acceleration of negative 0.42 radians per second squared. And why is it negative? Well, it's slowing down. That's why it's negative. Okay, then the next question is, how long did it take to come to rest? I'm going to change colors because, again, I'm running out of space here, so I'm going to change colors. Once again, we know what the acceleration is, and we know what the change in velocity was, and so that we can use that to come up with our time. So remember that acceleration is change in velocity over change in time. And our acceleration was a negative 0.42 radians per second squared. Our change in velocity was 89 radians per second, and that was a negative change, and that can give us the time. So now we just have to rework this equation and find time. So we're going to take negative 89, divide by negative 0.42, and we should get 211. And that is measured in seconds. Typically, though, when we talk about time, we're probably not going to say 211 seconds, so we really ought to change that to minutes. And so we're just going to divide by 60 and change it to minutes, and we get 3.53 minutes. The questions, again, angular acceleration, we have that. There's our angular acceleration. Second question was, how long did it take? And here is our time, so we got that. So we're finished with question number 2. All right, take a second to read question number 3. Okay, question number 3. Ladybug rests on the outer edge of a record, rotating at 45 revolutions per minute. If the diameter of the record is 25 centimeters, what is the linear velocity of the ladybug? What is the minimum coefficient of friction needed to keep the bug on the record? Okay, first of all, she is rotating at 45 revolutions per minute. We need to change that to radians per second. So 1 minute is equal to 60 seconds. And 1 revolution is equal to 2 pi radians. So we need to set up our unit conversion. We're going to cancel out the units, which we can cancel. So revolutions and revolutions cancels, minutes and minutes cancels, and we are left with radians per second. So go ahead and take a second to put that into your calculator, see what you get. All right, when you multiply that out, you should get 4.71 radians per second, and that is our velocity. If the diameter of the record is 25 centimeters, which means that the radius is 0.125 meters, then what is the linear velocity of the ladybug? One thing we can do is we can use that a little bit like we were doing before up here, that the angle times the radius would equal the linear distance. In a similar way, we can use the fact that angular velocity is equal to velocity over radius, or in other words, velocity is equal to the angular velocity times the radius. So here we have the angular velocity. We can find our linear velocity by taking that angular velocity and multiplying it by the radius. And the reason that we can do, because 0.125 is our radius, and a radius is like 1 radian. And so these radians can cancel, and we're left with meters per second. And so we go ahead and multiply that out on your calculator, and you should get 0.589 meters per second. That's our linear velocity. Now the second part of the question, what is the minimum coefficient of friction needed to keep the ladybug on the record? This is similar to a question we had on the last test, because the rotational unit and the circular unit are obviously very closely related. You're talking about things going in a circle or things rotating, and those are obviously going to be very similar. And so in this case, the force of friction is what is keeping it in the circle, and so we know that the centripetal force is mv squared over r, and we know that the force of friction is mu times mass times gravity. That's mu times the normal force. So our mass cancels out. That happens frequently. We are solving for the coefficient of friction. We're solving for mu. So I can divide both sides by g. And so I get v squared over g times r is going to be equal to my mu. And so now I just have to find those and plug them into the equation. So we get 0.589, and we're going to square that and put it over g times r, so 9.8 times 0.125. And so again, we're going to put that into our calculator, multiply that out, and you should find your mu. And so when you plug that in, you should get 0.28. So the coefficient of friction that is needed to keep the Ladybug on the record traveling at this speed is 0.28. Just a little piece of information is that 45 RPMs is the speed of a record player. There were two main sizes of records, and one of them was a 45. So 45 is the speed that a record player will move. Okay, last question, number 4. If the Ladybug moves halfway towards the center, what is the minimum coefficient of friction needed to keep it on the record? Okay, it's still going at 45 RPMs, but now she's in the center. And so she, being the Ladybug, she's in the center, and so her radius is different. So all these calculations are going to be different. So if she moves halfway into the middle, right, it says halfway towards the center, so she's going to cut that radius in half. So whereas the radius used to be 0.125, we need to cut that in half. So we take 0.125 and divide by 2. And so now our radius is 0.0625. So again, our angular speed is still the same, 4.71 radians per second. But the difference is we have a different radius. And so I'm going to use that equation I mentioned a little bit ago in the margin, and I'm going to change this over to linear velocity. And so we're going to take that 4.71 radians per second and multiply it by 0.0625. And when I do that, I'm going to multiply those out, and you should come up with 0.29 meters per second. So to figure out the minimum coefficient of friction in this case, I'm going to do the same setup. Centripetal force is equal to the frictional force. My masses cancel on each side. I can divide by g, and so I'm going to get mu should be equal to v squared over g times r. So let's go ahead and plug in here. Our v is 0.29. We need to square that. Our acceleration or gravity is still 9.8, and our radius is now cut in half, so it is 0.0625, and this will give us our new mu. So I'm going to plug this into my calculator and work it out. And so your new answer is 0.48. Okay, those are some examples of the different types of problems that we're going to encounter in this unit. There will be future worksheets and some problems that we'll work on that relate to these things, and all of these concepts are things you need to know. In the margins, a couple of those little shortcuts are helpful. The two main ones I tried to put in red here so you can see them. The one of them being that theta times r is the linear distance, and that omega is velocity over radius, or velocity is omega times radius. So make sure that you understand those. They're little shortcuts that you can use to make your problems a little bit easier.